Spectroscopy of atoms is very important in that we can learn about the electron structure of an atom. Spectroscopy also has the practical value of allowing the identification of substances present in a sample. In this lab, we will use spectroscopy to probe the electron structure of the hydrogen atom and identify substances in a fluorescent bulb and the sun. Though we refer to this as the handheld spectrometer, it is most convenient when used as a hands-free device set on a lab jack. The light from the source must enter the vertical slit located in the square molded in the plastic casing at the front right. When you look through the peephole, the diffraction grating spreads the light out into its component colors. A desk lamp is used to indirectly illuminate the wavelength and energy scales within. Here is a typical view through the grating. The upper scale is the photon energy in electron volts. The bottom scale is the wavelength of the light in nanometers. If you don't immediately see a rainbow of colors, try rotating the grating to make the grating lines vertical. As you rotate, you will see the spectrum rotate into view. Another cause of problems could be if you don't have the light streaming through the entrance slit to the right. Begin by just shining the incandescent bulb into the entrance slit. With the bulb as your source, you'll see all colors present in a continuous rainbow. Note the wavelength limits of each color. At what wavelength does red begin? At what wavelength does red turn to orange? Where does orange turn to yellow? This is somewhat subjective, of course, but will help you orient yourself to the spectrometer. Next, place a tube of hydrogen gas into the power supply. Be careful not to touch the high voltage electrodes of the power supply. It is rather unpleasant. Also, when you're finished, don't burn your fingers on the hot tube. Note the wavelengths and photon energies of each of the three prominent lines in the visible hydrogen spectrum. You should also acquire a hydrogen spectrum using the digital spectrometer. The light enters an optical fiber and is sent to the spectrometer. The digital spectrum appears as a plot of intensity versus wavelength, increasing to the right. Spectral lines appear as spikes in the spectrum. The wavelength of each line is measured by clicking on the line to position the vertical green indicator and noting the wavelength in nanometers at the lower left of the screen. According to the Bohr model, the hydrogen energy levels are discrete steps with energies of minus 13.6 electron volts, minus 13.6 over 4, minus 13.6 over 9, etc. In general, the electrons have an energy of minus 13.6 eV over n squared, where n is an integer. To remove an electron from the ground state of this potential energy well would require 13.6 eV of energy. This is the so-called ionization energy of hydrogen. According to the model, photons are emitted when an electron makes a downward transition from some upper level of n to a lower level. For example, an electron dropping from the n equals 3 level to n equals 2 will emit a photon with energy equal to E3 minus E2, which is 1.89 electron volts. The spectrum of visible photons emitted by hydrogen correspond to transitions from n equals 3, 4, 5, and 6, all ending at level 2. This gives rise to red photons, teal photons, violet photons, and from n equals 6 to n equals 2, a photon that is so violet as to be at the edge of the visible range, and not normally seen with these handheld spectrometers. With the digital spectrometer, you will be measuring only wavelengths. Wavelengths will need to be converted into photon energies. Since energy equals hc over lambda, the constants and conversions from nanometers to meters and joules to eV may be combined to give E in electron volts equals 1243 divided by lambda in nanometers. The differences in upper energy levels n equals 3, 4, and 5 and the lower energy level n equals 2 is E equals minus 13.6 over n upper squared plus 13.6 over 4. We can linearize the result if we plot E versus 1 over n squared. we expect a straight line with a slope equal to minus 13.6, the ionization energy of hydrogen. The y-intercept is expected to be 13.6 over 4, the energy of the lower n equals 2 level. Here is our plot of E versus 1 over n squared for the digitally obtained data. The handheld results will not be quite so accurate. The helium spectrum is more complicated because it has 2 electrons. Note the wavelengths of the 5 brightest lines. The Bohr model can only be applied to 1 electron atoms. Normal helium has 2 electrons, but ionized helium has a single electron and obeys a form of the Bohr model. The model must be adjusted to account for the presence of 2 protons in the nucleus, increasing the pull on the electron and increasing the negative energies of the electron levels by a factor of 4. Each energy is now minus 54.4 eV over n squared. Only one transition between these various levels corresponds to visible light. The rest are either UV or IR. By performing a series of trial and error calculations, you can identify which transition yields visible light. As a hint, looking at the energy scale in your handheld shows you that the visible light energies lie between about 1.8 and 3.0 electron volts. See if you can identify which of these lines was emitted by ionized helium and which upper and lower n values are involved. You may now proceed to acquire handheld and digital spectra from a variety of sources, recording the wavelengths of the prominent lines. When it comes to the mercury source, please be careful to have the glass in front of the source in place. Look at the very powerful UV line at the far left of this mercury spectrum when no glass is present. Those photons could damage your eyes. When the glass is in place, the mercury UV photons are absorbed. Sodium only has one prominent yellow line to record. Record the spectrum of a fluorescent bulb. Note that atomic emission lines are present along with a continuous background. The emission lines are emitted by the gas in the tube, and by comparison with other sources you have observed, you should be able to identify the gas. The continuous rainbow of colors is due to the fluorescent coating inside the tube, which converts ultraviolet emitted by the atoms in the gas into visible light photons. The warmth of color of the bulb is adjusted by just applying different coatings. Finally, obtain a spectrum of the daytime sky, which consists of scattered sunlight. If you're using the handheld, be careful not to aim at the sun, as you could easily damage your eyes. Here the lines are seen in absorption rather than emission. They appear as notches in a continuous background. Match wavelengths to identify and label the single sodium line, as well as the 3 hydrogen lines. You will have verified the presence of these elements in the photosphere of the sun.